times xc. And then we started having a discussion about what constraints you got imposed on these variables. And the main difficulty was because you had to ensure that every vertex is connected to every other vertex, right? So, and that was somehow difficult to ensure by if your variables were just these xe's. Okay, so the first step that we said is, you've got to ensure that the number of edges you pick is at least n minus 1. Right? Because if your number of edges is smaller than n minus 1, there is no way you can connect everything. Right? So this was the first constraint. So, and this you can express, right? So you can just say that sum over all edges of xe equals n. If you really want, you can put bigger than or equal to n minus 1, it doesn't matter. So that's something we did. Okay. And then we said that an example like this is bad because here you have 5 vertices and 4 edges. And I only drew the edges for which xe equals 1. Okay, and maybe there were other edges in the graph for which xe was 0. Okay, so there were other edges for which x prime was 0, and for these guys, let's say your solution put x equals 1. So now this clearly satisfies the first constraint, but this is not a valid solution to our problem because we haven't connected every vertex to every other vertex. Like this one is not connected to any of these. And then we had try 2, where we tried to add the constraint that there is at least one edge out of every vertex. That also is satisfied in this assignment, right? Because there are 2 edges from this guy, 2 edges from these things, and 1 edge from this one. But it's still not a valid solution. Okay. And then we had a suggestion which basically said that, okay, so you want to ensure that what you have is a tree. Right? So maybe you can add this constraint that says that for any cycle of size r, like this solution in particular is bad because here you have a cycle where all edges were chosen. Okay? You can say that maybe I will try to avoid doing that. So you can force the solution to be a tree by saying that in any cycle, you pick at most r minus 1 of the edges. So this is a valid constraint to add, and this will eliminate a bad solution like this. Okay, so far so good. But the only catch here is that now you have exponentially many constraints, right? Because in a general graph there can be exponentially many cycles. Like if you think of a complete graph, then basically a cycle for any subset to it. So all of a sudden you have exponentially many constraints for things of this kind. So these are things we saw. There was also a solution, alternate suggestion that somebody said, which is valid, but it was much more complex, right? So the solution was basically to make sure there's at least one path between any u to any v, and this was based on this homework problem that we saw about like taking powers of matrices. We said that this is a valid solution, but the constraints are not linear anymore if you do it like this. Okay, at least naive. Right, so that also happens to work. Okay, but again, this also is exponential. Okay, so this is roughly what we saw last class. So any questions on this before we move to the next one? Also, do we have the video set up? Yeah.
Assuming the size of the cycle is, for example, this is 3.
Yeah.
So it's a number of edges or number of.
Yeah, so here what you will have is, let's say I number the edges as 1, 2, 3, 4, 5, 6. Then your constraint will be something like x1 plus x2 plus x3 less than or equal to 2. So this will be one of the constraints that that your thing would have had. You would also have had a constraint corresponding to all of these edges, which would have said x1 plus x3 plus 4, 6, 5 is less than or equal to 4, for example. Yeah. Any other question? Okay. So it turns out that 1, 2, 3 together form a valid set of constraints for this problem. And the nice thing is that these are all linear constraints. There may be exponentially many of them, but they're still linear. I mean, each constraint is a linear constraint. And I also wanted to mention another canonical formulation that people often write for minimum spanning tree, which is this one. Okay, this is also exponential sized, but it is slightly simpler than the cycle formulation because at least you don't have to enumerate all cycles. So the way this one goes is you have one constraint for every subset of vertices, and this is based on the idea that if you have a spanning tree, then and if I take any subset S of the vertices, at least one of the edges going out of the set to the rest of the graph. Okay. So this is my rest of the graph. This is, let's say, E, and let's say I have like E1, E2, E3 going out from S to the rest of the graph. Then one of these edges must be picked. Okay, because if not, this would be a disconnected component. So you have a constraint of the kind xe1 plus xe2. Yeah, so it's a bit contentious if these are in any sense better than the cycle constraints, but you know, in some sense, at least they are different, right? And it turns out that having something like having a constraint like this, and each xe belongs to this 0, 1, and just trying to minimize E. So these actually turn out to be, oh, so this is not exactly this constraint, but it is meant. For all S, sum over E in edges out of S x E. Okay, so if you look at any S, you look at the set of all edges going out of S, and you take the sum of xe only over those edges, it must be at least 1. Okay, so that's and if you just have these constraints, note that this also encapsulates constraints of this kind, right? That one edge out of every vertex is chosen. Because if your S was a singleton, which is just this one vertex, then it's saying that all the edges going up, one of them must be chosen. At least one. So this captures constraint of the kind, and it also generalizes. And now you have exactly 2 to the size of V constraint. I mean, if you want to take it. Okay. So that's, yeah.
Do you not still need a constraint for the cycles here?
No, you don't need a cycle, any cycle constraint. Yeah, so let's see the why, right? So in fact, that was going to be my next point. For any formulation you write, you've got to show that this exactly captures your problem, right? So that's what we can see. So the validity of a formulation depends on proving that any feasible solution to the set of constraints you wrote down yields a valid solution to your original problem. Okay? And therefore, if you actually optimize it, so if you try to find the feasible solution with the least value, then you find the best solution. Okay? So you want to prove that any feasible solution to the set of constraints you wrote down yields a valid solution to the issue. Okay, so let's try doing this for these constraints. So consider the three constraints. Let's give these some names. So let's call this optimization problem as star. Consider any feasible solution to star. Okay. I want to claim that the set of is if S the set of it is let's call this X. X is the feasible solution. X is just a set of XE values. Okay. So just a bunch of XE values. That satisfy all the constraints. So if S denotes this for which XE equals 1, then S is a spanning tree. Okay, so this is the claim. So it's saying that you look at a feasible solution X to your problem. I mean, to this optimization formulation, which is something that satisfies these two inequalities. Okay, so each XE is 0, 1, and for any set S, this thing holds. Then we would like to say that if you just look at XE equals 1 values, then these guys form a spanning tree. And this will show that what we have is a valid, this will show the validity of this whole like 4-step process, right? Because if you have this claim, then any feasible solution that you get is actually a valid solution to the original problem. So if you minimize sum of WE XE over all the feasible solutions, then you get the minimum spanning tree. Okay. So this shows that the whole process is valid. Okay, so now how do we prove this thing? Yeah, I heard somebody say contradiction. I'm guessing so. Yeah. Okay. So yeah, let's try to prove this by contradiction. Let's say. Right? So suppose you take some feasible solution X. Nice thing is that these are all 0, 1 solutions. Right? So each XE is supposed to be 0, 1 in our formulation. So any solution you can just interpret it as this basically defined by S. So could it happen that S is not a spanning tree? Oh right. Okay. So maybe then so okay. Actually, you're right. So I have to be a bit careful on that. Then S. I don't want to say is a spanning tree. I want to say S includes a spanning tree. Okay, so I want to say that S contains a spanning tree, could contain more, but I would like to say that S at least contains a spanning tree. So, and remember that this is enough because you want to pick a set of edges so that every pair is connected to everybody else. You don't really need it to be a tree. The minimization will ensure that what you will get is a tree. Okay, because you want to minimize the sum of WEXE, and if you want to minimize it, it will ensure that what you get is actually a tree. Okay, so this is what we'd like to show, that any that if you have this set of edges, then it includes a spanning tree. Okay? So all you've got to show is that if you look at this set of edges, then every vertex is connected to every other. So this is equivalent to showing that using S, any vertex yeah, let me just write slightly differently. The graph with just the edges contains a path it's the same as saying that. I just rephrased it so that it looks nice. Okay, so it's like if you just look at the graph with the edges in S, then you have paths from every vertex. And this you can now prove it by contradiction. Right? So suppose not. Right? So if you did not have a path from U to V, what does it mean? So suppose there was some U, suppose there was some V. And let's say using these edges of S, there was no path from U to V. So there were some edges out of U which went somewhere, maybe there were some edges here. Maybe there was a cycle, doesn't matter. Right. So how do you now get a contradiction? So actually what does it mean to get a contradiction? Yeah?
You like assume what you're saying is false and then prove that that situation can't happen.
Right. So that's what I'm trying to assume, right? So I'm trying to say that this is what I would like to show, that the graph with just the edges in S contains a path between any two vertices. So I'm saying, yeah, let's assume that this doesn't hold. Let's assume that U and V are two vertices. Forget which one was V, maybe this one was V, right? So there was no path from U to V. Okay. And now, yeah, so what does it mean to obtain a contradiction? Assuming that.
So you probably want to start by assuming the constraints that we put on it on the previous slide. So like have some set S.
Right, so what you would like to show is that if there was no path between U and V, then some constraint was violated. So it could not have been that X was satisfying all the constraints. Okay. That would give a contradiction. Right? So that would show that any solution that satisfies all the constraints also has to have some path between U and V. Yeah.
So we have the constraint that at least one edge going out must be infinity, right? So if we consider just U and consider expanding the ball around that, right?
Mm-hmm.
So then we consider the other one, and then the other one turns out that somehow we should reach the V.
Okay, so he's trying to argue, give a reasoning for this. So before we get there, let me try to again just formally write down what you're saying. So we will argue that if there is no path from U to V, then there exists a constraint that is violated. Okay, so this is, and this gives a contradiction, right? So this contradicts the fact that X was the feasible solution. And now what he is arguing is, okay, so suppose there is no path from U to V, right? So here's U, here's V. So there's some set of vertices that you can reach, so that are reachable from U. So let's consider that set. Let's call it T. We know that T cannot include U. V, right? Because if T includes V, I mean this is the set of vertices that are reachable from U. Right? So if it included V, then there was a path from U to V. So, and we are assuming that there is no path from U to V. Okay. So yeah. So what do we do? So define T to reachable U using only the adjacents. Okay. So remember, S was the set that we defined earlier, right? So S is the set of edges for which X equals 1. Okay. And yeah.
Can you remind me one more time? So is the feasible solution, like, is the minimum spanning tree supposed to be like a strictly subset of the feasible solution?
Not a strict subset, it could be equal to that. But what we would like to say is that the edges that we pick, I mean, if you just look at the edges that we pick, you have a path between any two vertices U and V. And if you now try to, I mean, that was the official definition of the problem, right? So the formal definition of the problem just said that pick a subset of the edges such that all vertices are connected. Total weight of the edges should make this. So you don't, I mean, it just so happens that the optimal solution is a tree because all the weights are positive and there is no, and you can only gain by removing some edge. Right? So if there was a cycle. So is this question here? So he was asking, where are we actually ensuring that this is a tree? And the point is that we are not. All we are ensuring is that all vertices are connected to each other. Okay, so I'm defining T to be the set of all vertices reachable from U using only these as S. And yeah, so and now I would like to claim. One observation is that T does not contain V. Because we assumed that there was no path from U to V. And so it means that this the observation is now that out of T could have the value x equals 1. And this is kind of the key observation, okay, which is that if I define T this way, then none of the edges going out of T can have x equals 1. Why is that? Yeah?
Because then that vertex would be empty.
Yeah, so then that vertex would have been part of T. I defined T to be everybody that's reachable from T. So the fact that, just the definition of T implies that you cannot have something like that. And this gives a contradiction, because this implies that none of the edges out of T could have x equals 1. And remember, we had a constraint that said that for any set, let me replace this by T so that you don't get confused with the S that you see. So for any S, for any set T, at least one of the edges going out of this set is included, right? And we have exhibited a set where none of the edges going out is included. Okay. And that's the contradiction. Right? So we've come up with some constraints that's violated. I see some people not convinced, so I'll pause here for a bit and you can ask. Yeah?
You said that we don't need a constraint that ensures no cycles. Why is that?
Oh yeah. So this is going back to this question, I guess. So all I'm saying is that the definition of the problem just asks you to find a set of edges such that all the vertices are connected to one another, right? It's just that because our goal is minimizing the weights and these weights are all positive, the optimal solution will end up being a cycle. Will end up being a tree. It will not have cycles, because if it had a cycle, then removing one vertex or one edge would only improve the cost. Okay? So that's why you don't have to explicitly ensure. Yeah.
Can you explain then why in the previous version of the optimization problem you needed to specify the Taylor cycle?
Right. So in this version, we actually ensured that what you got was a tree, right? And where you had something like that, these three constraints, right? And so that's in some sense the reason I was not very satisfied with these set of constraints, because here somehow you're not focusing on the fact that these things are you are just ensuring on the number of edges being n-1 to force it to be something that connects everybody. Okay, so that's so if you, for instance, didn't have the first constraint, then you will not pick any of the edges, right? So that's an interesting point to think about, right? So these two sets of constraints both actually end up finding the minimum spanning tree, but somehow the philosophies are a little bit different. One tries to ensure that all vertices are connected. The other is trying to force your solution to be a tree that reaches everybody. So that's I guess a nice thing to know. Yeah, and this is very common in optimization formulations. You can actually write formulations of different kinds. Each has its own way of thinking of how you arrive at it, and both might be valid. Yeah.
So for the validity, shouldn't be if and only if, because you are saying that any physical solution is a valid solution, right? But there is a chance that we have several solutions, but it doesn't detect that solution, right?
Yeah, so you're right. I mean, in the sense that technically we should be able to say that, that's actually a very important point, maybe worthwhile spending some time on. So what he's saying is, you should not over constrain your problem, and that is something that you should also ensure, right? And this is true, you have to do it. It's just that in the way I wrote things, any true spanning tree actually gives a valid solution to this, right? So I must also prove that part to be formally correct. Okay. So let me do that. I was hoping that it's something that one can hand wave, but I mean it's good to be formal, right? So to prove the validity of the formulation, yeah. That for all the original problem optimization. So in some sense we are not over constrained. Right? So you can imagine, for instance, I can throw in arbitrary constraints, like I can just say that, oh, okay, some exactly one edge out of vertex u is chosen. Right? So this may not be true for the optimum solution. Okay, so there might be a spanning tree for which that's not true, right? But what I argued here will actually hold, right? Because now you have this extra constraint, and anything that satisfies the original set of constraints plus this extra constraint will also yield something as well. So in principle, yeah, so you should actually ensure that both directions work out. That the solutions to the two problems exactly correspond to one another. Okay. But often that direction would be the simple one. Often showing that these that whatever you wrote, and if you find something that's feasible to the optimization problem, going back, that's usually the tricky part. Yeah, so this is just something to keep in mind, that we should also ensure that we are not over-constrained. That is, any feasible solution to the original one remains feasible. Alright, so any other comments? Right, so again, this is the recap. So we have instance of problem, and we have this optimization formulation, and we want to typically ensure that solutions of the problem and solutions to the optimization instance, they are basically, there's a one-to-one correspondence between them. And that's how you often define variables and so on, place constraints. Okay, so let's now look a little bit about this part. Okay, so I want to say a few words just to give a sense of where is this paradigm useful. Right? So this is, so far we have seen that if you can, we've seen some examples of optimization formulations. We haven't spoken about when you can actually, when this is actually efficient. So I want to spend like a few minutes on this. Okay, so what optimization problems can be solved efficiently? Right, so it turns out that not much, at least if you want like provable guarantees. Okay, so in some sense, the main classes that we know to solve efficiently are these two fairly simple ones. So there are a few other exceptions, but more or less this is like, these are the only general statements we can make. So one example of problems that we can solve efficiently, so these are linear programs where you have real value variables, and constraints are linear, and the objective is also linear. Okay, so this we will see them in a little while. Okay, so the important thing here is that these are real value variables. So everything we've been seeing so far, we had this and this, but we had binary values, right? Like for both the set cover and the problem that we just solved. And yeah, so these can be solved in time polynomial in number of variables. Okay. So what we saw for minimum spanning tree is not great in that sense, right? Because you had exponentially many constraints. So there are tricks to get around this, but in general, this is what you can see. Okay, so the next class of problems, of which actually linear programs are a special case, are again you have real value variables, but now your constraints are a bit more general. Okay, so these are what are called convex constraints, which basically mean that your domain is your feasible set is convex. So you're optimizing over a set that basically that is convex, and I don't know if you guys remember, we saw the definition of convex maybe a few lectures ago. All it means is that if you have two feasible points, then the entire line segment joining these two feasible points is also feasible. Okay. So you don't have a situation like this. So this is not convex because you take 2 points here. The middle point, for instance, is not in the feasible set. Okay. So you can't optimize over domains that look like that. Okay. That might seem like a weird domain, but for instance, you can't optimize over the sphere if you don't include its interior. Okay. So if you want to optimize over just the sphere, you've got to include the interior as well. Okay. So there's a more natural thing where it looks round, but still you can't. It's not convex. Okay. So convex programs are again, yeah, you have your real value variables and you have convex constraint, and your goal is to minimize some convex objective function. Okay. And it's important that you want to minimize it, not maximize it or something else. Okay. Yeah, again, you will see these in ML courses, so let's not spend too much time on it. But it's easy to note that convex programs capture linear programs. Okay, so that's something that you should easily see. Okay, so that's so these are, I think, two general classes that we know how to solve well. Yeah.
If you're trying to maximize a concave function, does that ever show up?
Yeah, so maximizing a concave function is the same as minimizing a convex function, because negative of a concave function is convex. Okay, so they're both the same. Yeah. Anything else? Okay, so these are like provably efficient. Another class for which there are pretty good heuristics, and depending on whom you ask, some people think that these are easy. Things like integer linear programs. Okay, so these are the kind of things that we've been seeing, right? So your constraints and objective are all linear, but your variables could be binary. Okay, so or in general integer value. Okay. So here there is no, this is actually an NP-hard problem in general, so you can't have provably efficient algorithms, or at least we don't believe that, but there can still be, there's still pretty good heuristics for these. Okay, so there are ILP solvers that you can download and plug values into, and they will work for reasonably large values. In fact, people like NLP and so on, they often assume that ILPs are some alleviation. So, yeah, but again, in the worst case, they can be very difficult. And the same with quadratic programming, where you might have constraints that are linear, but your objective could be a quadratic objective. So this again can be difficult sometimes, but in general, there are pretty good heuristics for solving quadratic optimization. And there are also these whole solvers called QCQPs, which are like quadratically constrained quadratic programs, where your constraints are also quadratic. Okay, so this again, there are a lot of heuristics that people have studied for these kind of problems. So in general, if you can phrase a problem as simple enough constraints, chances are you should be able to feed them to a solver and get a reasonable solution. Okay, but we are not always guaranteed. The only ones for which we are guaranteed are linear dynamics. Okay. So I guess what you're asking is, most quadratic programming solvers have at least one subroutine that tries to convert it into a linear thing, and they often return the better of the things. And it depends on the problem. It depends on how they are solving these things. Yeah.
When you say linear constraints and linear objective functions, you mean the only operations you have are multiplying by constants and adding variables?
Yes. Oh yeah. So that's generally what I mean by linear. I just mean sums of variables. So sum of some ai x I is less than to bi, something like that. So those are the kind of constraints. Another thing that I'd just like to say is that most optimizers are some iterative algorithm. Okay, so they start with some solution, they slowly change it so that they get better. Okay, and eventually they converge, and that's the solution that's returned. There's some kind of local optimization type, local search type heuristics. So that's a very rough summary of optimizers. I did want to say a little bit more about linear programs because there's a nice geometric interpretation. And it also turns out that if you guys remember, we saw this problem very briefly called the maximum flow problem, right? So we had a graph, and you wanted to send some units of flow from U to V, and if you remember, flow was basically characterized by some value for every h. Okay, so dividing the space into like two regions, one region will satisfy the constraint, other region will not. And you have a bunch of these half spaces, and your feasible set is basically the intersection of these half spaces. Okay? And the feasible region for these things is often called a polytope. And now you want to minimize some linear function on a polytope, and it turns out that, so this actually is a fairly simple proof. You can show that optimum value is either infinite, plus minus infinity, or is attained some corner point. Okay. So in this example, if I wanted to maximize x1 plus x2, so the corner points of this polytope are these objects. Okay, so in this case, there are only two corners. The other corners are basically infinite. And what you can easily show is that for any objective function, either the optimum value is plus minus infinity, or it is attained at one of the corners. And this turns out to be a simple geometric fact. Like optimizing a linear function is like saying I want the extreme value in some direction. Like in this case, maybe the direction is something like this. And what is the extreme value in this direction? In this case, maybe it turns out to be this point. Okay, so yeah. Okay, so Again, I won't prove that, but it's somewhat easy to show. Okay, so the optimal is infinity. So most of the old algorithms for linear programming, the way they work is they find one corner point, then they try to move to a neighboring corner point that improves the value. Okay, so they basically do some kind of a local search over these corner points. And this is a clean, it's an iterative algorithm. And once you find, once you're at a corner point where you cannot improve your solution, you just stop and it turns out to be optimal. Okay? So this is called the Simplex algorithm. It works very well in practice. Okay, but slowly people realize that works well in practice, but it's not. But there are examples where this can take exponential time. Okay, so there is in the late 60s there was a very famous example called the clean minty cube, where people came up with people said that, oh, okay, here's an example where simplex algorithm can take exponential amount of time. So yeah, so for a long time it was open if you can provably solve linear programming in polynomial time. If you think about it, it's actually kind of not real to do this. And there was a breakthrough in the late 70s, in 79, which received a lot of attention. So here's like a article by somebody, and apparently so again, science in the 70s, 80s, there was a huge amount of Cold War and stuff, right? So linear programming was considered such an important problem that when like a Russian scientist came up with it, it was viewed as an analog of Sputnik, right? So and people were very worried that Soviets are so much ahead of us in terms of optimization, and there was a lot of worry. And yeah, so this is an article by one of the famous optimization folks, and yeah, he refers to this in the New York Times front page headline, right? So it made it to the headline. So it's probably the only time some algorithm made it to the front page of the New York Times. Maybe if you come up with something for factoring, it will make. Maybe actually the Shor's algorithm for quantum factoring may have made it. I'm not sure. So yeah. So anyway, so this is yeah. So it shows why linear programming was considered that important around that time, because everybody in optimization and operations research were using linear programming. Okay, and this is called Katian's algorithm. Okay, and this was in '79. Then, of course, somebody there was this person at Bell Labs who came up with an algorithm that was much faster than Katian's algorithm, and then people were happy that okay, somebody from Bell Labs came up with something much better, and this came up in '84. And actually, the reason I mentioned these is because these actually. They don't work by local search over the corners. Okay, so these are what are called interior point methods. And the way they work is actually, even though they want to find a point that's in the corner, they end up moving within the polytope a little bit. And then they end up at the corner. Okay, so and which is a weird thing to do, because you know that your solution is a corner point, but you still end up going through the interior, and so you might end up at like some suboptimal points, but you will eventually. So yeah, in hindsight, there is no reason why you should restrict yourself to corners, right? It's just that it was simple algorithm to do, but yeah, and it's not clear how you move in the interior. So this was the novelty of these guys' algorithms. But again, these are also iterative methods, and they converge in polynomial time. But a lot of the LP solvers that you will see in practice, like in MATLAB and so on, they still use Simplex for most for most problems. All right, so that's good. So for the last 10 or so minutes, so let's ask, okay, so far I've said that if you have linear programs and you have a continuous domain, then you can solve it efficiently. Does this sort of a thing have any applications to combinatorial problems? Right? So if you remember, all set cover, matching, and so on, all our variables were binary, right? And so there is this divide, right? Like when we tried to phrase our interesting problems as optimization, we ended up with like binary valued problems. But the only ones that we know how to solve efficiently are these continuous domain problems. Okay? So the one question you can ask is, are these algorithms still useful? Right? So can you use, so in particular, can LP for solving and this is something people wrestled with for a while. Like in the 70s, it was, I mean, so one kind of problems people considered are, problems where you can be guaranteed that the corners are all integer points. Okay? So for some problems, all corners are binary values. Okay, so for that I have to mention what it means by relaxation. Okay, so let's do a simple example. Okay, so I will start with this vertex cover example. Okay, and if you prefer, I can do set cover as well, but vertex cover is easy. So let me define the problem again. So if you recall, this was we saw this in homework 3 when you had some streets and you wanted to monitor it. We said that this is a special case of the set cover problem. Right? So basically the problem is you have a graph. Okay, unweighted, undirected, something, and you want to select subset of vertices of min possible size such that every edge is covered behind one of its corners. Okay, so this is the goal in this vertex cover problem. Okay, so you're given some graph and you just want to pick a small subset of vertices so that for every edge, one of its endpoints is selected. Okay. And like we saw in the homework, this is a special case of the set cover. And you can now write problem. I mean, you can write it as an optimization formulation, exactly the same way as we did for set cover. So you can have for each vertex a variable xu, and this is supposed to be 0, 1. And so these are variables, constraint. You have one constraint per edge. xu plus at least one of its endpoints must be chosen. And your goal is to minimize the total number of things that you've chosen. So your objective is minimize sum over all u. Okay. So this is an optimization problem, but you have binary variables, and but your constraints are linear, and your objective is a linear objective. So is this formulation clear to everyone? So this is basically the formulation we saw for set color that I ended up writing. Okay. So good. So all is good with this formulation except for the fact that these are supposed to be binary. So one common way to convert this sort of an object or optimization problem to a continuous one is the natural thing you would think, which is I replace this constraint with 0 less than or equal to xu less than or equal to 1. Okay. So now I allow xu to be fractional, but it's some number between 0 and 1. Okay. So this is called a relaxation. So we have this discrete optimization problem. So we have original. Okay, so here we had some constraints, some objective, and we had xu belong to 0, 1. And this is called the linear programming relaxation. So you have same objective, same constraints, but you replace these the domain constraints with x u less. So it's called a relaxation because you are relaxing this last constraint. Instead of it just asking you to be the corners, either 0 or 1, you allow anything in between. Yeah.
But since we know that our optimum values are at at corners, we're still going to end up with.
So I will come to that. Yeah. So yeah, but is the notion of a relaxation clear to everyone? Okay. So this is something you can do for any optimization problem. Right? So for any like discrete optimization problem, if your objective and constraints happen to be linear, then you can convert it into a linear program by replacing those constraints with these ones. Okay. And a lot of the early work basically said, okay, so now let's look at the LP relaxation. So and just now think of it geometrically, right? So you have some constraints, and these are defining some equations. And we said that this is the feasible region for this. So we said that geometrically it looks like an intersection of hash. Now, suppose it were true that every corner point of this actually has 0, 1 coordinates. So let's call this corner point some x. xu belongs to 0. Then we are done. Right? So then we are in good shape. right? Because we know that the optimum solution will be one of the corner points. And it so happens that for every corner point, all the coordinates are binary. So I can pretend that those constraints don't really matter, right? Because I will anyway have xu being 0 or 1. So this turns out to be true for some problems, but it's not true all the time. Can you guys see why this may not be true for vertex cover? Or actually, I mean, even if it were true, why this is not obvious? I mean, to answer this, you have to think about what is a corner point, right? Like intuitively, what is a corner point? Like in this, actually, let's go back to the simple 2D example that we saw. Like here, you had a bunch of constraints, and in 2D, corner point was some place where two constraints met. That's how you can define corner points in general. So now, the problem is you have a bunch of constraints. And these are constraints of the forms from xi plus xj bigger than or equal to 1. And these are constraints of the form some xu less than or equal to 1, xu bigger than or equal to 0, and so on. Now, if you took the intersection of constraints of this kind, then it's great. Wherever they meet are all integer points. But if you look at some constraints of the first kind, places where they meet may not actually be integer. Okay? So if you solve for xi plus xj equals 1 and some, let's take 3 of such constraints, you will have all halves as a solution or something like this. Okay? So we'll see an example of that in the next class. Okay? So problems, there are a few problems for which you can prove formally that every corner point is an integer point. For those points, for such problems, turns out that linear programming relaxations are great. You can just pretend that you are solving the corresponding integer optimization formulation, and you can just read off the solution. Okay, but there are problems like vertex cover where what you get if you solve the relaxation will not actually be an integer point, and there you have to do something called rounding to actually try to convert it to a corner point, to like an integer point. And then you might lose some factor in the approximation. Okay, so we'll see that a little bit in the next class, okay, which is next Thursday.